Okay, let's jump into the second part here with 3.6. We got another example, and I'm going to use the whiteboard just because it will lead me a little bit. Actually, you know what? Let's try to do it here. We'll try both ways, see kind of what works out the best. Yeah, let's just use the whiteboard. Sorry, I'm kind of doing this on the fly. Okay, the equation is, I already forget it. Is it x over? Yep. X over radical x squared plus 2. Okay, let me full screen this here. Double check. You're looking at the whiteboard. Okay. So let's talk about the just standard basic stuff here. We got our x-intercept. Our x-intercept is where the equation would equal 0. So when would x over radical x squared plus 2 equals 0? Well, that's when we can cancel out the bottom there. We don't have to worry about that. When would x equal 0? Well, that's when x equals 0. So x-intercept is at 0, comma, and then we're going to plug that in. What is 0 over the square root of 0 squared plus 2? That'd be 0 over the square root of 2, which is just 0. All right, the y-intercept is when does this equation, where does this equation equal 0? When x equals 0. And when x equals 0, if we plug 0 in, that's also 0. Okay, so the x and y intercepts are at 0, 0. Next point, I think we need to talk about the limits, right? Limits as we start on the left side, and the limit as we start on the right side of the equation. Okay, so we need to go through and look at these degrees here since we do have a fraction. We got a degree 1 on the top, and technically we have a degree 1 on the bottom. All right, so when these are the same degrees and we have a radical here, we have to go through. Remember, the trick is we're going to divide them out. Now, this is where you might want to use a graphing calculator here, and this would be something I could really go through. Now, both of these are 1 over 1, so they're going to be the same thing. And then you have to remember with the negative, infinity is going to go to the negative one side, but you know, graphing calculator is here to help us out. So we're going to start getting into problems that are a little bit more difficult. All right, I'm going to hopefully you guys can see this here. You know, I'll switch over here. We'll go to our equation here. We got x divided by, and then I'm going to put it in the square root of x squared plus 2, I think it was. Graph. All right, so you can see on the bottom it's going towards -1. On the top it's going towards +1. And we can see our graph, it looks very simple. So we will get some complicated math, but our graph is going to be simple. So remember, we're not using the equation to get the answers or the graphing calculator to give us the answers. We're using it to help verify our thoughts and our hypotheses here. So it does go towards -1 here, and it does go to +1. So we talked about vertical asymptotes and horizontal asymptotes. This must be the A here. All right, vertical asymptotes. We would see when does the denominator equal 0. And we actually don't have to worry about that here. Because if we get rid of the square root, we're going to be asking when does x squared equal -2, and we can't take the square root of -2. So there are no vertical asymptotes, which we didn't see any on our picture. And then horizontal asymptotes, we actually have 2. We have one when y goes towards -1 and y goes towards +1. Okay, next is the extrema? I think so. All right, so the extremas, we have to do the first and second derivative test. So I'm going to clear off some room here. You guys can see and this is where it gets a little, I don't know, for me already. I look at that and I go, man, that graph was super easy. The derivatives are not going to tell us too much, but it's still going to get an answer here, and it's going to be complicated because we have such a weird formula. Now, what we could do is a couple different things. We could change this problem into x divided by x squared plus 2 to the 1/2 power, and we'd have to do low d high, high d low, all over low low. Or we can actually make this x times x squared plus 2 to the -1/2 power. And then we only have to do the product rule. You can pick your poison. I kind of like doing this problem here, so I'm going to do it that way. I'm going to use just the product rule, and then I'll rewrite it once I get that finished. All right, so product rule says we'll take the derivative of x, which is 1. We'll leave the x squared plus 2 to the negative 1/2 power alone. All right, now we're going to leave the x alone, and we'll take the derivative of the second part, which is, okay, we put the negative 1/2 in front. We leave the inside part alone. We drop that down a power to negative 3/2 power. Then we times by the derivative of the inside. The derivative of x squared plus 2 is 2x. Okay, so still working on the first derivative. What we're going to do now is we're going to factor out that x squared plus 2 to the negative 3/2 power from both this term and this term. If we take the negative 3/2 power away from the negative 1/2, it actually bumps it up to a positive 1 power. So that becomes an x squared plus 2. And then over here, if we take away it, this goes away and we're left with the x and the negative 1/2 and the 2x. So x times a negative 1/2 times 2 is a negative x squared. So this kind of simplifies down to, well, that kind of goes away. We get x squared plus 2 times to the negative 3/2 power times 2, or that is just 2 over x squared plus 2 to the 3/2 power. Okay, so let's talk about this first derivative. Do we have any critical numbers? First derivative, make your number line. So the first derivative is when the derivative equals 0. So one does 2 over x squared plus 2 to the 3/2 power equals 0. Well, when we look at the top, can the top ever equal 0? Can the 2 ever equal 0? No, it cannot. So there's no critical numbers on the top. We also want to check the bottom. Can x squared plus 2 to the 3/2 power equal 0? Well, we can take this to the 2/3 power. X squared plus 2 would still have to equal 0. X squared would have to equal negative 2, and we can't take the square root of negative 2. So there are no critical numbers on the first derivative. So that means the graph is going in the same direction. This graph is either always positive or always negative. So we get to pick any number here and plug it into the first derivative to see what the graph is going to do. And I'm going to pick 0 because that's the easiest number. What's 2 divided by 0 squared plus 2 to the 2 or 3/2 power? Well, that's going to be 2 on the top, and then on the bottom here, we'd have 0 plus 2. 2 to the 3/2 power is like 2 radical 2. If we take 2 and divide it by 2 radical 2, it's still just going to be a positive number. So that graph is always going up, which we actually saw looking at the graphing calculator. I don't know if that just popped up or not, but you can see that graph is always going up. Okay, let's go ahead now. And let me try to clear off some room here. Get rid of that. I'm going to move this first derivative. I actually do like both of those. Oh, I didn't mean to do that. No. It's okay. Didn't mean to make it all crazy here. Let's get rid of that. Oh, man. I'm picking the wrong numbers. I think I might be moving too quick here. Move all that stuff out of the way. Okay, so there's the first derivative. All right, second derivative. If we want to do the second derivative, we can do the derivative of this part here, or we can do the derivative of this part here. I'm going to do, let's do quotient rule because we didn't do quotient rule, and it's actually not going to work out too bad. All right, so quotient rule, we have low, which is x squared plus 2 to the 3/2 power, d high. Well, the derivative of 2 is 0, so that's going to go away. That's nice. Minus high is 2, and then d low, we got to do the chain rule of. So the bottom here is we got 3/2 of the x squared plus 2 to the 1/2 power times the derivative of the inside. The derivative of x squared plus 2 is 2x. And then all over low. If we have the 3/2 power and we have another 3/2 power, that would be 6/2, or aka the third power. Okay, let's clean this up. So this is going to go away because that's times 0. So really we have 2 times 3/2, which is just 3. We got negative here, and then times 2. So we would have negative 6x times x squared plus 2 to the 1/2 power over x squared plus 3, or x squared plus 2 to the 3rd power. And the last thing we can do here is we can actually factor this out. If we take a 1/2 power away from this, we're going to get a negative 6x over a x squared plus 2 to the 5/2 power. This was 3 or 6/2. If we took away the 1/2 from the top, it drops it down to the 5/2 power. Okay, so there's the second derivative. Let's do the second derivative test. Now, typically, I don't like to put it above the first derivative test, but I'm just kind of running out of room. So where does the second derivative, negative 6x over x squared plus 2 to the 5/2 power, equals 0? Well, first we have a critical number when the top equals 0. When does negative 6x equal 0? And that's easy. That's when x equals 0. The other time is when the bottom, x squared plus 2 to the 5/2 power equals 0, which we already know, okay, that's not going to work. So there's only one critical number, that's at 0. All right, now we need to determine the curvature, whether that is concave up or concave down. So we're going to pick a number less than 0 and a number bigger than 0, and we're going to plug them into the second derivative. So number less than 0, how about negative 1? What's negative 6 times negative 1 over negative 1 squared plus 2 to the 5/2 power? Okay, let's try to think about this logically here. Negative 6 times negative 1, that's a positive number. If we over here, we'd have, okay, that'd be 1 plus 2, that's 3. We take the square root of any number, it's going to stay positive. And if we take to the 5th power, it's going to stay positive. So this bottom's always going to be positive. Now the top here, the negative 6 times the negative 1 is positive. A positive divided by a positive is positive. So that's concave up, which we actually solved from the graph that we used. Then at 0, we pick a number bigger than 0. How about 1? If we just switch this to a positive 1, all that is going to do is not going to change the bottom at all. The bottom's still going to be a positive, whatever number that is, positive 3 to the 5/2 power. Now the top is going to be negative 6. Negative divided by a positive is a negative. So the graph is always going up, but it switches from curving up to curving down at 0. All right, so let's clear this all out. No, actually, I don't want to clear this all out. I want to basically make some room here. Just move that over. Second derivative, I want to keep it, I didn't want to expand that out. I wanted to keep it out over here. There we go. Let's talk about this. We need to talk about the extrema, right? That's the last thing we need to do. So we got mins, we have maxes, and we have points of inflection. Those are the extrema that we're looking for in this class. The mins and maxes are found by critical numbers on the first derivative. There are no critical numbers on the first derivative, so we don't have any mins, we don't have any maxes. Our points of inflections are critical numbers on the second derivative that actually exist. We have a critical number on the second derivative, 0, and 0 is a point. So the point of inflection is at 0. We'd have to plug it back into the original equation to find out its location, or we actually look, it is our x-intercept, it is our y-intercept. That's 0, 0. So let's graph this out here. This graph is going to be very easy to do. We only need to go on the y-axis down to -1 to +1 because we have our horizontal asymptotes, our end behavior graphs that we're going to look at here. We could make them go all the way across, but really since it's only to -1 on the left side, we only need to have the left side at -1, and it's only +1 on the right side, so we only need that at +1. The other thing that we need to mark here on our graph is our x-intercept, our y-intercept, and it ends up being our point of inflection at 0, 0. So we want to make sure that that's marked. And then we're going to follow our graph. The graph is always going to be going up. So even though our end behavior here is towards -1, our graph is going to be going up from this direction, and it is going to be curved up until we get to 0. Then after 0, we're going to switch to curve down, but still be going up. So we're curving it down, but it's going up still. And there's our equation. So you can see here, this is a great example of, we probably could have done this without using a graphing calculator, but having a graphing calculator is a tool that we can use to help us out. All right, let's do one more problem from our notes and we'll probably end this video. Oop, let me go through, I got to change my screen share here, share. All right, so let's do the next one. All right, x times x minus 4 to the third power. Okay, oops. All right, so here's the equation. X times x minus 4 to the third power. All right, you know what I'm going to do here? I'm going to pull up the graphing calculator as well. There we go. And let's just graph this so we kind of get a heads up of what we're looking at. X times x minus 4 to the third power. Okay, so it looked like this graph went down. There's like a minimum here, pretty low, and then it goes up, and then we have this like kind of flat curved part where it changes. It's not a min, it's not a max. It looks like probably a point of inflection here, and then it keeps going up. So we kind of know like the end behavior here. It starts up high, ends up high, which will make sense too. Let me look through this. Okay, so let's go to our whiteboard. Let's start doing the work here. Oop, I'm clicking all the wrong buttons. All right, let's take care of our basic stuff, our x-intercept and our y-intercept. Our x-intercept is when the original equation equals 0. Well, this is already factored, so that's nice. So we know that x equals 0 is an x-intercept. And then we got to figure out, okay, when does x minus 4 cubed equal 0? And that's pretty easy. That's when x equals positive 4. So we actually have two x-intercepts, and we saw in our graph it did cross the x-intercept at 0 and 4. And if we plug those back in, it'd be at 0, 0, and 4, 0, because that's the x-intercept. It's when the y equals 0. The y-intercept is when the x equals 0. So we plug x back into the original equation. If we plug x back into or 0 into the original equation, that ends up being 0 times 0 minus 4, that's 0. Okay, so not too bad. All right, the limit we saw from our graph here, from the left side and from the right side, that this end behavior is up towards infinity. Now, the reason why is technically, if we were to like FOIL this all out, we would have, this would be some x cubed times x. We would have an x to the 4th power over x to the 0 power. 4 is bigger than 0, so it would be infinity. And since it's an even degree, it's going to be up at infinity, both of those. Okay, next we have vertical asymptotes and horizontal asymptotes. Well, there is no denominator here on this problem, so there's no point where the equation would not exist. So there is no vertical asymptote. Horizontal asymptote, our limits are not going towards any single number. Remember, horizontal asymptotes can only be found when our limits are going towards a specific number, so we don't have any of those. All righty, let's, maybe we can just erase this here, isn't too much. All right, now we get to do the fun stuff. We get to do the derivative tests. You know what I'm going to do? I'm going to make a first derivative number line here. Probably need more room than that. And then I'm just going to put a second derivative one here, just because I know I'll need both of them. All righty, first derivative. And we could FOIL this all out, but I'm going to leave it in this term because, you know, we're fairly good at the product rule now. All right, what's x times, okay, so we got to do product rule. Take the derivative of x as 1. We'll leave the x minus 4 to the 3rd power alone. Now we'll leave the x alone, and we'll take the derivative of the x minus 4 to the 3rd power. That is 3 of the x minus 4 to the 2nd, times by the derivative of the inside. The inside, x minus 4 is just 1. Okay, so this is why it's always important here that we factor out the common term. The common term is the x minus 4 squared. It's the lowest between the two. And we get left here. This would just be an x minus 4 to the 1st power. And over here, if we get rid of the x minus 4 squared, we're left with the x times 3 times 1. So that's a 3x. So the first derivative here is x minus 4 squared times 4x minus 4. Okay. So here's our equation. We could change the order of that either, but we got to figure out now with our first derivative test, when does x minus 4 squared times 4x minus 4 equals 0? Well, this is great. This is why we didn't want to FOIL this all out, because this is already factored. All we need to do is to take each one of these factors and set them equal to 0. All right, so this one's easy. We add the 4 over. Okay, x equals 4 is a critical number. This one here, we got to add the 4 over, then divide by the 4. So we got 1. So we have two critical numbers on the first derivative. One's at 1, the other one's at 4. We now need to determine the direction of the graph. Now, we probably could look at the equation to see, okay, the graph went down and went up and then had a dip and then went up again. So we probably know that it's going to go negative, positive, positive, but let's verify that by plugging those numbers in. So I'm going to pick a number less than 1. 0 is always a great one. All right, so let's see, 0 minus 4 squared times 4 times 0 minus 4. All right, 0 minus 4 squared is negative 4. Negative 4 squared is 16. 16 times 0 minus 4, that's 0 minus 4. Okay, that'd be negative 4. 16 times negative 4, that's a negative 64. So it's negative. The graph went down like we thought. Okay, now picking a number in between 1 and 4. I'm going to stick with 2 because it might be easier. All right, 2 minus 4 squared times 4 times 2 minus 4. All right, let's see, 2 minus 4 squared, that's negative 2 times, or negative 2 squared is 4. And 4 times 2 is 8. 8 minus 4 is also 4. 4 times 4 is positive 16, so the graph is going up. Then pick a number bigger than 4. I'll pick 5. All right, so 5 minus 4 is 1. 1 squared is 1. Times 4 times 5 is 20. 20 minus 4 is 16. That's a positive number. So like we said, the graph went down, it went up, and then it went up again. But we still have critical numbers at 1 and 4. Okay, so let's clear off this work here. Let's move on to the second derivative. All right, I'm going to just kind of see if I can make this go away. Push that up there. Okay. Second derivative time. All right, we're going to take the derivative of the derivative. Now I'm going to do this part first and then that part, just because I always like to leave the chain rule at the end. All right, so I'll take the derivative of 4x minus 4, which is just 4. We'll leave the x minus 4 squared alone. All right, now I'll leave the 4x minus 4 alone. We'll take the derivative of the other side, which we got to do the chain rule. So it becomes 2 of the x minus 4 to the first power times by the derivative of the inside, which is 1. Okay, so we do need to factor this out. We factor out the common term, which is just an x minus 4 to the first power. And then we're going to see what left over we get. Okay, we would have a 4 times x minus 4 to the first power if we got rid of an x minus 4 from this part here. And then over here, we would be left with the 2 times the 4x minus 4. Okay, so we do have a lot of things that we need to clean up over here. All right, let's distribute this out and see what we got. 4 times x is 4x, minus 4 times 4 is 16. All right, now if we distribute the 2, we get plus 8x and then minus 8. Okay, so the second derivative comes out to be x minus 4. And then over here, we would get 12x minus 24. Is that what it is? Yeah. Okay, so we got to do second derivative critical numbers. So when does x minus 4 times 12x minus 24 equals 0? This is great. It's already factored. We just got to figure out when x minus 4 equals 0, which we've done this already. That's when x equals 4. The other one we got to do is when does 12x minus 24 equals 0? And that's when 12x equals 24, and that's when x equals 2. So we got two critical numbers. One is at 4, and the other one is at 2. Okay, so now what we need to do is to plug some numbers in here to see out what's the concavity. We can always look back at the graph to help us think. The graph like had definitely a curved up, and then it switched to curve down, and then it went back to curve up. So I think it's going to go positive, negative, positive, but let's verify that by plugging numbers in. So I'm going to pick a number less than 2. 0 is going to be fine. I'm going to plug it into the second derivative. So what's 0 minus 4 times 12 times 0 minus 24? All right, that's going to be a negative 4 times, that's going to be negative 24. Negative times a negative is a positive. Okay, pick a number in between 2 and 4. Okay, so 3 is the easiest one. So 3 minus 4, that's a negative 1, times a 12 times 3 minus 24. That would be 36 minus 24, that would be a 12. A negative 1 times a positive 12 is a negative number. Then pick a number bigger than 4. How about 5? 5 minus 4, which is 1, times 12 times 5, 60 minus 24. All right, so that's like 60 minus 24. What is that, 36? 1 times 36, that's a positive. So yep, it went positive, negative, positive. Okay, so we have all of our information here. Let's kind of clear this up a little bit. Gonna move some stuff around here. Maybe I'll erase some things. Can I erase? I know sometimes when I get so much writing, the erasing just kind of lags, but this seems to be going all right. And then here's the second derivative, all nice and neat. Move up here. Oh, yeah. Okay, so let's talk about our extrema that we have. Oh, what do we do? There we go. That's nice. Our extrema, which is our mins, our maxes, and our points of inflection. All right, so our mins or maxes are critical numbers on the first derivative. Now, we do have a critical number at 1, we have a critical number at 4, but our mins or maxes are where it changes direction. So we do have a change in direction from going down to up at 1. Going down to up would be a min. And then we have a no maxes. Even though it goes up and changes here, that doesn't change. Our points of inflection are our second derivative critical numbers that exist. And both of these do exist. So we have 2 points of inflections. One's at 2 and the other one's at 4. Okay, so we don't have any maxes here on the graph or any relative maxes. We actually have to find the mins here. And to find the location, like before they were nice, they were already ones we already on here. What we need to do is take this x value and plug it back into the original problem to figure out where its y is at. So what's f of 1? Not f prime, well, it's just f of 1. What's 1 times 1 minus 4 cubed? So let's see, that would be negative 3 cubed. That'd be negative 27. So we have a min at 1, negative 27. And then we have some points of inflection here. We'll plug in 2. What's 2 times 2 minus 4 cubed? Let's see, that's 2 times 4. 2 minus 4 is negative 2. Negative 2 cubed is negative 8. So that'd be negative 16. And then if we plug in 4, which we already did, 4 would be at 0. Move. Okay. So let's go through and now let's see, can we graph this? I'm going to erase this. I actually don't need that one here. I already have the second derivative. All right, how do we get a graph of this? And so this is where our graphs can be somewhat liberal. We just need to make sure we plot all these information and we label it accordingly. So we could make a scale that goes all the way down to negative 27 and then we can plot those out. Or if we just go through and make our chart here, our x-intercept, we have one at 0, 0. We have a y-intercept at 4, 0. Let's see, or we have 2 x-intercepts, 0 and 4, 0. We have y-intercept at 0, 0. We have some mins at 1, negative 27. Now that's the lowest point here. So if I just say like over here, 1, negative 27. And we know 1 is to the right of 0 and to the left of 4, and negative 27 is below that. We have 1 at 2, negative 16. So somewhere in between here, you know, just taking some guesses here. 2, negative 16. And then we got another one at 4, 0. Okay, so I'd say this is a pretty good point that we need to have. Now there's no vertical asymptotes, no horizontal asymptotes, so we just need to make sure we draw the lines that connect. Our graph on the left side is going to start up at positive infinity, so we should start up high. Our graph is going to go down until we get to 1 and then switch going up. And the whole time until we get to that, it's going to be curved up. So I'm actually going to make this go backwards here. So we're going to go through that point. Here we go. Not the best straight line, but I'm trying my best on the computer here. The graph is going down direction, but it's curved up. All right, now after 1, it's going to be curved, or it's going to be going up until it gets to 2, it's curved up. So, okay, going up, curved up. Then in between 2 and 4, the graph is going up, but curved down. So we can have our, you know, we have our split in our graph here. So you can see kind of how we have this point of inflection that changes the curvature. It doesn't change the direction, just the curvature of the graph. All right, now at 4, the graph is going to be going up because it's a positive first derivative and curved up. So after 4, going up, curved up, that looks like that. And we end at positive infinity. And there's our graph. It matched what we have on our graphing calculator. Now this graph isn't drawn to scale, but we get a general idea of what's going on here. So this is the 3.6 notes. You guys have a big section and homework here of 3.6, and we're all just going to group it together. Your tests are going to be problems that are like this. You're going to have some problems that you're going to be able to use a graphing calculator on to help you feel better about it, and then other problems without a graphing calculator. So best of luck on this. Take your time with this. Definitely make sure you guys understand all these concepts and write down any steps on a piece of paper. Who knows, you might be able to use it. All right. Thanks for watching, guys. Have a great one, and I will see you next time.